In this lesson, we will discuss logistic regression. We will start by introducing the sigmoid function, which helps modeling probabilities, set up the objective function, discuss how logistic regression is different from linear regression, generative versus discriminative models, and the strengths and weaknesses of logistic regression. Logistic regression is a classification model where the key idea is to transform any real value y into a probability value between 0 and 1. The sigmoid function, denoted by sigma of z, is given by this formula: e to the power z over e to the power z plus 1, takes any real value z and maps it to a value between 0 and 1. Let's take a look at this graph. So for large positive values of z, the output is going to be close to 1. And for large negative values of z, the function is going to give a value closer to 0. Notice when z equals to 0, meaning that there is a 50-50 chance for either class. Consider a binary classification problem like spam versus not spam. In the training dataset, 0 for not spam and 1 is for spam. The goal is to model this relationship using a function like f theta of x, which in its simplest form is just a linear model. And logistic regression assumes that we choose the parameters w and b in a way that if y equals to 1 and the email is a spam, we want z to be very large, so close to 1. But if y equals 0, then p of y equals 0 given x is 1 minus theta of z. Now we discuss how to set up the objective function for logistic regression. For probability of y equals 1, given the input features, this probability is modeled using this sigmoid function, where w0, w1, all the way to wn are the parameters that we are trying to learn from the data. Next, let's consider a single data point with features xi and a class label yi. This means that the probability of being 1 is p of I, and the probability of being 0 is 1 minus p of I. This follows a Bernoulli distribution, which is commonly used in binary classification tasks. But since our output variable yi hat is binary, either 0 or 1, we can write the probability of a given class as yi equals 1, then the equation simplifies to p of I, or if y of I equals to 0, then the equation simplifies to 1 minus p of I. At this point, we have defined our objective function, and the next step is to optimize it using the maximum likelihood estimation and gradient descent. We start with the probability of the predicted label yi hat being equal to the actual label yi. And this is the likelihood function for a single observation based on the Bernoulli distribution. Then, since we assume that our training samples are independent, then the probability of the entire data set, the likelihood, is the product of the individual probabilities. We want to maximize the likelihood function to find the best model parameters, so we express our likelihood in terms of the logistic sigmoid function. And it turned out that instead of maximizing the likelihood it's much easier to minimize the negative log likelihood. And this function measures how well our model predicts the labels. Finally, substituting the terms, we will get a formula, and then we apply the gradient descent to solve this formula and get the parameters. What is the difference between linear regression and logistic regression? In linear regression, y, the target variable, is continuous value ranging from -infinity to infinity. And some of the examples are predicting house prices, predicting temperatures, stock prices, sales, and so on. On the other hand, logistic regression is used when our target variable is categorical, meaning it belongs to a discrete set of classes. And the output is presented as a probability representation. So it's going to say that the closer the value, let's say to 1, that means, this is a spam, and closer to 0, not spam. Some of the application, spam detection, disease diagnosis, sentiment analysis, and so on. More comments on logistic regression. It can handle multiple types of features, computationally efficient, interpretable, and most importantly, it generalizes very well, especially when the relationship between the features and output is not clearly linear. Also, logistic regression outputs a probability score, which gives a confidence in the prediction. Also, the weights can be helpful to make a statement about the effectiveness of each features. However, the disadvantages of logistic regression, it doesn't work well when the boundary is not linear. So it's great as much as the boundary is linear and the data is separable. Here's a summary slide about binary classification. So we have f of x, which is a linear function, and the prediction is based on this f of x. If f of x is greater than 0, then we get one class, which is the x is a class. And if f of x is less than 0, then we get the O's class. Some classical linear classifiers are logistic regression, linear discriminant analysis LDA, perceptron, and support vector machine. Now we get to a key and insightful question. So suppose that we have more than one linear model. Which one is better? In this visualization, we have 3 classifiers, H1, H2, H3. H3 is clearly inaccurate, so we're going to drop it. But between H1 and H2, both of them correctly classified the data, but we need to pick the model that has better margins. So H1 seems like it barely classified those 2 points correctly, whereas H2 comfortably separated data sets. So we need to look at these margins and try to maximize the margin value for the classifier. Another distinctive issue in the topic of classification is whether the classifier is generative or discriminative. Generative classifiers like naive Bayes or Bayesian networks model how the data is generated. We compute likelihoods and then we pick the one with higher probability. On the other hand, discriminative classifiers model a probability of y given x, and it uses the data to create a decision boundary, then uses this decision boundary for classification, like logistic regression and support vector machines. strengths and weaknesses of discriminative classifiers generally have higher prediction accuracy in comparison to generative models, more robust for noise or error in the training data, faster evaluation. However, these models take long time to train, often hard to interpret these functions, and it's difficult to incorporate in domain knowledge because it's unlike generative models where we can integrate priors in data or distributions. In summary, we discussed logistic regression, problem formulation, sigmoid function, expressing probabilities, and the strengths and the weaknesses of discriminative classifiers.